In the unending quiet of the cosmos, there are moments that whisper, and then there are moments that scream across the void. This is the story of one such scream. A star, a celestial titan that had burned for millions of years, had reached the end of its magnificent violent life. From a distance of 21 million light-years away in the spiral arm of a galaxy we call the pinwheel, a new point of light suddenly ferociously appeared. It was not the gentle birth of a new sun. It was a death, the most spectacular demise the universe can orchestrate. This is the chronicle of Supernova 2024ggi. And this is the tale of its very first day. A day when its ghost light, twisted and shaped by the explosion, began a journey to our world, carrying the intimate secrets of its own destruction. To comprehend the magnitude of this cosmic detonation, we must first journey back in time, long before the final fateful second. We must travel to a place of serene beauty, a grand designed spiral galaxy, a celestial island of over 1 trillion stars, known to us as NGC 5457. It hangs in the constellation Ursa Major, a glittering pinwheel of stellar nurseries and ancient dying luminaries. Among its countless inhabitants was one particular solar behemoth, a red supergiant, swollen and unstable, living on borrowed time. For millennia, it had been a colossal furnace, a factory of the elements. Imagine a smithy, not of iron and steel, but of cosmic matter itself. In the heart of this star, the core, the pressure and temperature were so extreme that they defied all terrestrial comparison. This was the anvil of creation. Here, for millions of years, hydrogen atoms, the universe's simplest building blocks, were relentlessly forged into helium, releasing a torrent of energy that pushed back against the star's own immense gravity. This titanic struggle, a delicate and long-standing equilibrium, was the source of the star's brilliance, its very lifeblood. But this process of creation was also a countdown to annihilation. As the hydrogen fuel in the core was exhausted, the forge grew hotter. The star's heart contracted, its gravitational pull intensifying, cranking up the temperature and pressure to unimaginable new levels. A new phase of fusion ignited. Helium atoms, the ash of the first fire, now became the fuel hammered together to create carbon and oxygen. The stellar entity swelled its outer layers, expanding and cooling, transforming it into the bloated crimson giant that it was in its final days. Its structure became a cosmic onion, a series of concentric shells, each one a different crucible burning a heavier element. A layer of hydrogen burning into helium surrounded a shell of helium burning into carbon, which in turn encased a layer of carbon fusion, and so on. Deeper and deeper into the star's heart, the process escalated, creating neon, magnesium, silicon, and finally, at its very center, the ultimate ash of this thermonuclear inferno, iron. The creation of iron is a profound and fatal turning point for a massive star. Every fusion reaction up to this point had produced a net release of energy, the very energy that held the star up against its own crushing mass. Fusing iron, however, does not release energy, it consumes it. The central forge, the engine at the heart of the star, had run out of fuel. The pillar of light and pressure that had supported trillions upon trillions of tons of matter for eons simply switched off. The delicate balance was broken irretrievably. Gravity, the silent, patient victor in all cosmic struggles, had finally won the war. What happened next occurred with a speed that is difficult to comprehend. The iron core, an object larger than our planet Earth, but compressed to a density of thousands of tons per cubic centimeter, lost all its support. The star began to fall inward on itself. To visualize this moment, picture the tallest skyscraper ever conceived by humankind. Imagine it stands 1 million miles high, a testament to impossible engineering. For ages, its colossal internal supports have borne its weight. Now, in an instant, in less than a single heartbeat, every one of those supports across every floor vanishes simultaneously. The top of the structure begins to plummet downwards, accelerating under its own phenomenal weight. It is a freefall of unimaginable scale. The outer layers of the star, the vast shells of silicon, oxygen, and hydrogen, began their catastrophic descent toward the center. They reached speeds of over 70,000 kilometers per second, a significant fraction of the speed of light. The entire celestial body, a magnificent object, millions of times the volume of our Sun was collapsing into a space smaller than a city. As the core was crushed beyond all limits, protons and electrons were forced together to form neutrons, releasing a flood of ethereal particles called neutrinos. In that single terrible instant, the neutrino burst, carried away more energy than our own Sun will radiate in its entire 10 billion year lifetime. This torrent of neutrinos, ghost-like particles that rarely interact with matter, was so dense that it blasted through the infalling stellar material, depositing just enough energy to re-energize a stalled shockwave. The implosion hit the impossibly dense neutron core and did something extraordinary. It bounced. This rebound, this titanic shockwave, was the true beginning of the supernova. It was the collapsing skyscraper having pancaked at the bottom, now exploding outwards with a fury that beggars belief. The shockwave tore through the descending layers of the star, heating them to billions of degrees. A wave of incandescent destruction raced from the core to the surface. This was nucleosynthesis on a scale never seen in the star's life. The shockwave itself was a travelling forge, smashing atoms together to create elements heavier than iron, silver, gold, platinum, uranium. The very elements that we consider precious and rare on Earth were being manufactured by the quintillion ton in the heart of this dying giant. Finally, after a journey that took mere hours, the shockwave reached the star's surface. The moment it broke through, the photosphere is known as the shock breakout. It was the first light of the supernova, an eruption of high-energy gamma rays and X-rays, a flash of brilliance that briefly outshone its entire host galaxy. The star as it had been was no more. In its place was an expanding fireball of cosmic shrapnel, a roiling, seething cloud of newly forged elements, blazing with the light of 100 billion suns. And this light, this final glorious message from a dead star, began its long, lonely voyage. For 21 million years it travelled, crossing the desolate expanse between galaxies, a silent testament to a cataclysm long past. It journeyed through epochs of terrestrial history, unseen, unheard. It passed by the Earth when our distant ancestors were first walking upright. It continued on as civilizations rose and fell, as empires were built and turned to dust. And then, on a clear spring night in the year 2024, it arrived. The initial detection was not made by a human eye. It came from the unblinking robotic gaze of an automated sky survey, a machine programmed to tirelessly chart the changing heavens. An algorithm comparing a fresh digital image of the Pinwheel galaxy with reference images from nights before flagged a new anomaly. A single, unfamiliar pixel brighter than it should be. An alert, coded and impersonal, flashed across a network connecting observatories and astronomers across the globe. A potential supernova. Candidate designation 2024ggi. The coordinates were broadcast and a quiet, urgent race began. In professional observatories from the peaks of Chile to the dormant volcanoes of Hawaii, telescope operators received the notification. Schedules were hastily rearranged. Targets were reprioritized. Massive instruments, mirrors the size of living rooms, swiveled with ponderous grace, their domes humming as they opened to the cold night air, all turning to focus on that one specific point. Simultaneously, dedicated amateur astronomers, the sentinels of the night sky, were alerted. In backyard observatories and remote dark sky sites, they too pointed their equipment toward Ursa Major, eager to confirm the discovery to be among the first humans to witness this new fleeting star. The data began to pour in. Spectrographs were attached to the telescope's instruments that act like prisms, splitting the supernova's light into its constituent colors, its rainbow barcode. The very first spectra confirmed its nature. Strong absorption lines of hydrogen were present, the clear signature of a Type II supernova, the death of a massive star, its outer hydrogen envelope torn asunder in the blast. The initial reports painted a picture of a standard, albeit spectacular cosmic event, but some teams were preparing for a different kind of observation. They were not just interested in the brightness or the color of the light. They were preparing to ask a more subtle, more profound question. They were going to measure its polarization. Light, as we learn, travels as a wave. But this is an oversimplification. It is an electromagnetic wave, with electric and magnetic fields oscillating at right angles to its direction of travel. For a moment, let us set aside the complexities of electromagnetism and imagine a simpler, more tangible analogy. Think of a long rope tied to a distant wall. You hold one end and begin shaking it up and down. A wave travels along the rope, a perfect vertical oscillation. Now you shake it side to side. Another wave travels, but this time it's a horizontal oscillation. Light from an ordinary source, like a light bulb or the surface of a star, is like shaking that rope in every direction at once. Up, down, left, right, and every conceivable angle in between. The waves are a chaotic, jumbled mess of orientations. This is unpolarized light. Now imagine you place a picket fence between you and the wall. The fence has vertical slats. If you shake the rope up and down, the wave passes through the gaps cleanly. But if you shake it side to side, the wave hits the slats and is blocked. The fence has filtered the waves, allowing only those with a specific orientation to pass through. It has polarized the wave. A polarizing filter does the exact same thing to light. It is a microscopic picket fence, a grid of molecules all aligned in one direction. It absorbs light waves oscillating in one plane while allowing waves oscillating in the perpendicular plane to pass through. This is why polarized sunglasses work so well to cut glare. Sunlight reflecting off a horizontal surface like a road or a body of water becomes partially polarized in the horizontal direction. The sunglasses have vertical polarizers, a picket fence that blocks this horizontal glare, allowing only the vertically polarized ambient light through. For astronomers, polarization is a tool of almost magical power. It allows them to see the unseen. It reveals shape and geometry in objects that are so distant they appear as mere points of light. Consider the light from the supernova. If the explosion were a perfectly symmetrical event, a flawless expanding sphere, the light coming directly towards us would be a jumble of all polarizations. Any light that was scattered would be scattered from all sides of the sphere equally. The horizontal components would cancel out the vertical components. The diagonal components would cancel out their counterparts. The net result would be zero polarization, a perfectly unpolarized signal. But what if the explosion was not perfect? What if it was messy, lopsided, asymmetrical? What if the star before it died had shed its outer layers, creating a dense, donut-shaped disk of gas around its equator? Or what if the explosion itself was not a sphere, but was shaped more like a colossal dumbbell with two powerful jets of material blasting out from the poles, while the equatorial regions expanded more slowly? In such a scenario, the geometry is broken. The light from the incandescent fireball would illuminate this surrounding debris cloud. Photons would scatter off the electrons in the gas. This scattering process naturally polarizes light. If we are viewing this lopsided event from the side, more light will scatter from the regions above and below the disk than from the obstructed front and back. This imbalance would create a net polarization. The light reaching Earth would no longer be a random jumble. It would carry a subtle but measurable preferred orientation. It would be a faint signal, a whisper encoded within the supernova's roar, a ghost image of the explosion's true misshapen form. Measuring this on day one, when the outermost layers of the exploding star are still visible before the fireball expands and becomes more uniform, is the Holy Grail. It offers a pristine, direct snapshot of the cataclysm's initial geometry. And so, as telescopes gathered the first photons from SN 2024ggi, specialized instruments called polarimeters were brought online. These devices are exquisitely sensitive, capable of detecting even the slightest preference in the orientation of light waves arriving from across intergalactic space. The data began to accumulate a stream of numbers, representing light intensity measured through filters oriented at different angles. In the control rooms, an atmosphere of tense anticipation settled. The raw numbers were fed into computers, which worked to subtract the background polarization from our own galaxy, filtering out the noise to find the signal. Then the result appeared on the screen. It was astonishing. The light from SN 2024ggi was not unpolarized. It was not even weakly polarized. On its very first day, the supernova exhibited a significant degree of polarization, one of the highest ever recorded for such an event at such an early stage. The picket fence of the cosmos had revealed a profound secret. The death of this star had been anything but a serene, symmetrical event. It had been a chaotic, violent, and fundamentally lopsided affair. The numbers on the screen were more than just data. They were the first brushstrokes of a portrait of a cosmic monster. Astronomers began to model the explosion using the polarization data to reconstruct a three-dimensional picture of the event. The picture that emerged was breathtaking. The expanding fireball was not a sphere, it was profoundly oblate, squashed as if by an invisible cosmic hand. The models suggested a large-scale asymmetry, perhaps an enormous loop of ejected material, a colossal arc of stellar plasma containing the mass of several suns hurled preferentially in one direction. This was not the neat, tidy explosion often depicted in animations. This was a tangled, brutal conflagration. It implied that something had profoundly shaped the final moments of the star's life and the initial moments of its death. What could cause such a dramatic asymmetry? The clues pointed back to the progenitor, the red supergiant itself. Perhaps the star had been spinning incredibly rapidly before its demise. This rotation would have created a centrifugal force flattening the star at its poles and causing it to bulge at its equator. When the core collapsed, this rotational energy would have been conserved, funneling the explosive force outwards along the path of least resistance, away from the dense equatorial plane and out through the poles, creating a naturally elongated asymmetrical blast. This was a compelling and elegant hypothesis. But another more tantalizing possibility existed. What if the progenitor star was not alone? Many, if not most, massive stars are born in binary or multiple star systems. They spend their lives locked in a gravitational dance with a companion. The presence of a nearby stellar partner could have had dramatic consequences. As the red supergiant swelled in its final phases, it might have begun to spill its outer hydrogen envelope onto its companion star. This mass transfer would have stripped material away from the supergiant, creating a complex swirling disk of gas and dust engulfing both stars. This circumstellar medium would have been a thick, messy environment far from a pristine vacuum. When the supernova finally detonated, the shockwave would not have expanded into empty space. It would have slammed into this pre-existing wall of gas. The interaction would have been spectacular and deeply asymmetrical. The dense equatorial disk would have confined the explosion, squeezing it and forcing it to expand more rapidly in the polar directions. The polarized light, then, was not just a map of the explosion itself. It was a ghost image of the star's lost companion, a shadow cast by a dance partner, whose presence was only revealed at the moment of death. The fresh footage, the data from day one, was a window into this complex dynamic history. It was a form of cosmic archaeology, using the light from the destruction to excavate the structure of what came before. The ongoing observation of SN 2024ggi became a global obsession. Every day, as the fireball expanded and cooled, its characteristics changed. The initial highly polarized light began to fade as the ejector grew larger and more diffuse, its initial shape becoming less distinct. But the story was far from over. The light we see today is just the beginning. For years, for decades to come, we will watch the aftermath of this explosion unfold. We will watch as the fastest moving clumps of ejecta, those hurled out in the asymmetrical blast, catch up with and slam into the slower moving shells of gas the star shed thousands of years before it died. These collisions will create new shockwaves, new brilliant flashes of light that will illuminate the star's history like cosmic lightning flashes. We are watching in real time the creation of a supernova remnant, an expanding celestial shroud like the famous Crab Nebula, a monument to a star that died almost 1,000 years ago. SN 2024ggi is giving us the chance to see the first stages of such a remnant's birth. And within that expanding cloud of gas and radiation is a treasure of immense value. The elements. Every atom of gold in a wedding ring, every trace of silver in a photograph, every bit of uranium that fuels a power plant was born in a cataclysm exactly like the one we are now witnessing from a safe distance. Our sun is not a first-generation star. It is too rich in heavy elements. It could only have formed from the recycled ashes of previous generations of massive stars that lived, died, and seeded the interstellar medium with the fruits of their nuclear furnaces. SN 2024ggi is not just an object of scientific curiosity, it is a direct link to our own origins. The iron atoms at the core of the hemoglobin molecules carrying oxygen through our blood, were forged in the heart of a star like this one. The calcium that gives our bones their strength was synthesized in the final explosive moments of such a celestial body. When we look at the fading light from this supernova, we are in a very literal sense looking at the forge of our own creation. We are stardust observing the birth of more stardust. This single distant event reinforces the most profound lesson of astronomy, the lesson of connection. The universe is not a collection of disparate, isolated objects. It is a single, vast, interconnected ecosystem, operating on scales of time and space that challenge our intuition. The death of a star 21 million light-years away is not a foreign event. It is part of the same grand cosmic cycle of death and rebirth that ultimately led to the formation of our solar system, our planet, and our own existence. The study of supernovae, like 2024ggi, also has implications that reach to the very edges of cosmological understanding. While this Type II supernova is fascinating for its physics, its cousins, the Type Ia supernovae, are the universe's most crucial yardsticks. These events, which result from the explosion of white dwarf stars, have a remarkably consistent peak brightness. This consistency allows them to be used as standard candles. By measuring their apparent brightness from Earth, we can calculate their distance with incredible precision, allowing us to map the three-dimensional structure of the cosmos. It was by using these standard candles that astronomers in the late 1992 made the shocking discovery that the expansion of the universe is accelerating, driven by a mysterious repulsive force we now call dark energy. Our entire model of the cosmos, its history, and its ultimate fate rests upon our understanding of these stellar explosions. But what if there are subtle variations? What if some explosions are not perfectly standard? By studying close-by events like SN 2024ggi in excruciating detail, by understanding the messy physics of asymmetry of companion, interactions of progenitor environments, we can refine our models. For all supernovae, we learn to spot the subtle signs of an atypical event, allowing us to better calibrate our cosmic distance ladder. The secrets revealed by the polarized light of this one explosion will ripple outwards, strengthening the foundations upon which our entire comprehension of the universe is built. What then is the ultimate legacy of this single point of light? For the astronomers who captured its first photons, it is a career-defining event, a puzzle box of data that will be analyzed and debated for years. For science, it is a crucial piece of evidence, a test for our theories of stellar evolution, and a new benchmark for our understanding of cosmic explosions. For the Pinwheel Galaxy, it is a small, violent wound that will slowly heal, leaving behind a beautiful, expanding nebula, and at its heart either a super-dense neutron star, or if the progenitor was massive enough, a brand new black hole, a tear in the fabric of space-time itself. But for humanity, for us, its meaning is perhaps more philosophical. It is a reminder of the universe's sheer scale and its relentless dynamism. The cosmos is not a static, unchanging backdrop. It is a place of violent transformation, of constant creation and destruction. To witness a supernova, even as a faint speck of light, is to be granted a momentary glimpse into the engine room of reality. It is a humbling experience, a powerful antidote to the terrestrial concerns that so often occupy our minds. It connects us to a story that is billions of years old, a narrative written in the language of light and gravity. As the weeks turn into months, SN 2024ggi will slowly fade from view, its peak brilliance dimming as its ejector expands and thins. But its journey in our scientific consciousness is just beginning. The light from its heart continues to travel outwards, not just towards us, but in all directions, an expanding sphere of information. In a few thousand years, this light will reach other stars within the Pinwheel Galaxy, perhaps illuminating other worlds appearing in alien skies as a temporary brilliant new star. The matter ejected from the explosion, a cloud of heavy elements, will drift through interstellar space for millions of years more. Slowly, imperceptibly, it will mix with vast clouds of hydrogen gas. Gravity will eventually pull this enriched material together, and in the distant future, new stars and new planets will coalesce from the debris. perhaps on one of those future worlds life will arise. And perhaps that life made from the very atoms of SN 2024ggi will evolve to a point of intelligence where it can build telescopes and look up at the sky wondering where it came from. The scream has faded to a whisper. But the echo, the legacy of that one brilliant catastrophic day, will resonate through the cosmos for all time. It is an echo of endings and a promise of new beginnings.